Yeah, good evening to all. This is Navneet Krishnan from iitiansgateclasses. In this section, we'll be dealing with GATE 2017 flight aircraft stability problems. A total of 9 marks has been asked from this topic. Okay. GATE 2017, question number 10. To ensure longitudinal stability and not the condition of equilibrium of a low-speed aircraft, the aircraft components must be designed to satisfy which one of the following conditions. Option A, dou Cm by dou alpha less than 0 and Cm not greater than 0. Option B, dou Cm by dou alpha less than 0. Option C, dou Cm by dou Cl less than 0 and Cm not less than 0. Option D, dou Cm by dou Cl less than 0 equal to 0. For longitudinal stability, Cm versus alpha, the plot should be like this. For longitudinal stability and for the condition of equilibrium and to trim at positive angle, Cm naught should be greater than 0 and dou Cm by dou alpha should be less than 0. Okay. For longitudinal condition, for longitudinal stability, Cm naught should be greater than 0. It is Cm naught should be greater than 0 in order to trim at positive angle. That is in order to achieve equilibrium condition. Okay. For stability alone, dou Cm by dou alpha less than 0 is enough. Okay. For aircraft to be stable, dou Cm by dou alpha less than 0 is enough. But to trim at positive angle and to achieve equilibrium, Cm not greater than 0 also required. Okay. So option B is the correct answer. If we have to ensure equilibrium also, then option A is correct. If we have to ensure equilibrium also, then option A is correct. If we have to only achieve longitudinal stability but not the condition of equilibrium, second condition itself enough. That is dou Cm by dou alpha less than 0 is itself enough. Next. Question number 12. GATE 2017. Question number 12. Let Nm and N0 be respectively non-dimensional locations of stick-fixed maneuver point and stick-fixed neutral point of a low-speed conventional aircraft. The distance measured with respect to nose of the fuselage. The numerical values of Nm bar minus Nm bar naught. Option A will always be negative, will always be positive, will always be 0, can have any value depending upon the location of center of gravity. If you see the maneuvering neutral point HM, where HN is the stick fixed neutral point, this is stick fixed maneuvering point. That is V bar A1 by 2 mu. V bar is nothing but your VH, which is ST into LT by S into C. Okay, C bar, mean aerodynamic bar. Where A1 is the tail lift coefficient AT, dou CLT by dou alpha T. Okay. Mu is nothing but aircraft relative density. Mu is nothing but aircraft relative density given by W by rho GS into LT. W by rho GS into LT. Okay. So if I substitute in this, HM minus H is equal to V bar by A1 by 2 mu. Here, for our condition, they have given it as HM as Nm bar, non-dimensionless location as Nm bar, and the neutral point location as Nn bar. That is equal to V bar A1 by 2 mu. If you see, tail volume coefficient is always positive. tail lift off slope is always positive, and mu, the aircraft relative density is always positive. That means this value will be always greater than 0. That means it is positive. If I have to consider for the stick free condition, same thing holds good. So only thing is the changes for stick free condition is compared to this is for stick free condition, the stick free maneuvering point equal to stick free neutral point plus V bar into A1 by 2 mu into 1 minus A2 by A1 into B2 by B1. Sorry, B1 by B2 into B1 by B2. Where A1 is the tail lift coefficient again, which is dou CLT by dou alpha T. And A2 is nothing but elevator effectiveness, dou CLT by dou del D. B1 is nothing but dou CHE by dou alpha dash. B2 is nothing but dou CHE by dou del D. Floating tendency, and this is called as restoring tendency. Floating tendency, and this one is restoring tendency. The value of HM dash minus HN dash is nothing but V bar A1 by 2 mu into 1 minus A2 by A1 into B1 by B2, where this value 1 minus A2 by A1 into B1 by B2 is a free elevator factor F, which will be always less than 1. That means overall value has become, compared to stick fixed condition, compared to stick fixed condition, the overall value has become less, but still it holds positive. So it is less than 0. It is less than, sorry, it is greater than 0 only, but still compared to stick free neutral point, stick fixed neutral point, this has got reduced, because stick fixed neutral point as stick free neutral point value also got reduced, stick free maneuvering point also got reduced. Thereby this value will get reduced, but still remains positive by a factor. How much it gets reduced is by the factor F. That much it gets reduced. So the option is will always be positive. Any doubt? Where mu is again aircraft relative density, which is nothing but W by rho G S into LT, where LT is the tail lift arm. Okay. Next. Question number 13. The phenomena of rudder lock in conventional low-speed aircraft is primarily due to option A, large values of directional derivative. Option B, side wash due to fuselage on vertical stabilizer. Option C, tendency of rudder to float rapidly at high angles of side slip. Option D, side wash due to wing on the vertical stabilizer. If you see, rudder lock is a phenomena which, by the definition itself, it occurs by the tendency of rudder to float at high angles of side slip. Now, what happens is, if I draw a plot between rudder angle and the yaw angle, the rudder angle to produce the required yaw angle linearly varies. But due to side slip and all, and due to the flotation, what happens? It will not actually be linear. It follows this trend because rudder is floating. So this is the rudder angle required. This is the trend for rudder angle required for required yaw angle. But since it is floating, what happens? This is the flotation angle of the rudder. This is the flotation angle of the rudder. Flotation angle of the rudder. Okay. This is the required rudder force to be produced by the pilot to supply that. Pilot has to supply that force in order to deflect the control surface. This corresponding position is called as rudder lock. This corresponding position is called as rudder lock. Okay. If what happens, at very high angles of side slip, the floating angle will catch up the required angle at which pedal force must be 0. Here the floating angle and the required rudder angle is coincides. That means the required rudder force is 0. At this point, the required rudder force is 0. If the side slip is increased beyond this point, if the side slip is increased beyond this point, what happens? The pedal force will reverse. If the side slip is increased beyond this point, the pedal force will reverse. And what happens? The rudder will continue to deflect. What happens is the rudder continues to deflect and locks in this position like this. In order to break this lock, a considerable amount of force is required. If we have to break this lock, a considerable amount of force is required. So rudder lock is not. It should be avoided at the design stage itself, or it should be made such a way that rudder lock is not a usual phenomena occurring. Okay, so how to reduce this rudder lock phenomena? How to avoid this rudder lock phenomena? Now, what happens? First way to reduce the rudder lock is reduce the rudder effectiveness. Reduce the rudder effectiveness. When you reduce the rudder effectiveness, what happens? You require thereby what happens? We have to increase the rudder deflection at a given side slip. Because if you have to provide considerable amount of yaw, we have to increase the rudder deflection to rudder deflection at any given side slip. Okay. So if you reduce the rudder effectiveness, what happens? That means rudder is undersized. That means what happens? It requires larger amount of deflection for the same amount of yaw. So thereby we can reduce the rudder lock phenomena. Or provide a dorsal fin. What is dorsal fin? You take your aircraft. This part of the body is called as dorsal fin. This part of the body is called as dorsal fin. Dorsal fin is also a small auxiliary airfoil. What happens now? When you have dorsal fin, it increases the fuselage stability. That is, it increases the fuselage directional stability at very high angles of side slip. It increases the fuselage stability at very high angles of side slip, and also reduces the vertical tail to stall at very high angle. Okay. It also reduces the tendency of vertical tail to stall at very high angle. Thereby, it avoids rudder lock phenomena. So, if you use these two phenomena, then we can reduce the rudder lock phenomena considerably. Okay. So, for this, the only option is the tendency of the rudder to float rapidly at high angles of side slip is by definition is called as rudder lock. Okay. Any doubts? Next. An aircraft model was tested in a low-speed wind tunnel at a Reynolds number of 2 into 10 power 6 based on the wing mean curve. The variation of pitching moment with angle of attack alpha for two elevator deflections are recorded as recorded during the test is presented below. They are given for an elevator deflection of minus 10 degree, Cm naught value is 0.03. For the elevator deflection of 0 degree, Cm naught value is 0.02. Based on the result presented in the figure above, the value of elevator control power in per radian will be dash as per 3 decimal places. Okay. Now, if you see what is elevator power, dou Cm by dou del E is called elevator power, which is nothing but minus neta T into Vh into dou Clt by dou del E, where this is the elevator effectiveness, dou Clt by dou del E is the elevator effectiveness, this is the elevator power. This is the elevator power. Okay. Now, if I have to solve this, what happens? Now, dou Cm by dou del E can be written as Cm2 minus Cm1 by del E2 minus del E1. Can be written like that. Here, Cm2 is 0.03, Cm1 is 0.02. 0.03 minus 0.02 divided by del E2 is corresponding deflection is minus 10, del E1 is 0. So, minus 10 minus 0. So, we will get it as minus of 0.001 minus of 001 per degree. If I have to convert into radian, per radian, then I have to multiply it by 180 by 5. If I have to convert it by per radian, I have to multiply it by 180 by 5. So value we get is minus 0.00 minus 0.0573 per radian. If I round off to 3 decimal places, it is minus 0.057 per radian. So the answer is minus 0.057 per radian. Any doubt? Next question. The roots obtained by solving longitudinal characteristic equation of motion for a statically stable aircraft are given as follows. Lambda 1 comma 2 is minus 0.02 plus or minus 0.38. Lambda 3 comma 4 is minus 2 plus or minus 2.5i, where I is equal to root of minus 1. The undamped short period longitudinal natural frequency and damping ratio in that order are close to option A 3.4 and 0.73, option B 3.36 and 0.65, option C 3.83 and 0.56, option D 3.2 and 0.63. So first, one of the eigenvalues corresponds to Fugite motion, other eigenvalue corresponds to short period oscillation. Okay. Now, time period for that oscillation is 2 pi T cap by Q. Okay. Where T cap is the airplane relative mass by rho Vs. So, if I Q is the imaginary part of the solution. So, for 1 comma 2, T time period is nothing but 2 pi by 0.3 into T cap, which is 20.943 T cap. Second time period, second thing if you take T3 comma 4, it is 2 pi by 2.5 is the imaginary part into T cap. So it is 2.513 T cap. That means time period for this eigenvalues is small. That means this corresponds to short period. If the time period is low, that is called a short period. So this is the solution of short period oscillation. So lambda 3 comma 4 is the short corresponds to short period oscillation. Okay, lambda 3 comma 4 corresponds to short period oscillation. Now from this we have to find out what is the eigenvalue, what is the natural frequency, what is the damping ratio. Okay. Now from lambda 3 comma 4, how we can write is the quadratic equation can be written as s square into lambda 3 plus lambda 4 into s plus lambda 3 into lambda 4, that is equal to 0. Okay. So if I substitute lambda 3 plus lambda 4, what happens? This is minus 2 minus 2. If I add it, it will become minus 4. If I add the imaginary part, one imaginary part is plus 2.5, other imaginary point is minus 2.5. If I add both, it will become 0. So lambda 3 plus 4 is this one. Plus lambda 3 into lambda 4, which is minus 2.2 plus, so lambda 3 is nothing but minus 2 plus 2.5y. Lambda 4 is nothing but minus 2 minus 2.5y. It is a plus b into a minus b. So we can write a square minus b square. Okay. We can write it as a square minus b square. Okay. So the a square value is minus 2 into minus 2. So it will become plus 4 into plus 4 minus into 2.5 into minus 2.5. So it will become minus 6.25 equal to 0. So this can be written as s square plus 4s plus minus into minus, it will become plus. So it will become 10.25. It is in the form of s square plus 2 zeta omega n s plus omega n square equal to 0. So if I equate these two, that is omega n square equal to 10.25. So we get undamped natural frequency as omega n to be root of 10.25, which is 3.201 radian per second. Okay. If I equate the next two, these two, what happens? 2 zeta omega n equal to 4. We know omega n is equal to 3.201. Substituting that, I get zeta as 4 divided by 2 into 3.201. That is equal to 0.625, approximately 0.63, which is an underdamped solution. Okay. So 0.60 is the damping ratio. Natural frequency is 3.201 radian per second. So answer is first natural frequency, next damping ratio. So natural frequency is 3.2 and 0.63. So option D is the correct answer. Any doubt? Okay. Next. Question number 44. A conventional aircraft was analyzed to estimate contribution of wing towards Cm naught, that is Cm at alpha equal to 0 of the whole aircraft. The wing was installed with 0 setting angle along the fuselage, that is IW is 0, wing setting angle is 0. along the fuselage reference line. Further, wing was laid such that x bar AC equal to 0.3, x bar CG equal to 0.4, x bar AC and x bar CG are non-dimensional distances from leading edge to the leading edge of the wing of the aerodynamic center of the wing and CG of the aircraft respectively. The wing had following aerodynamic characteristics: CL naught equal to 0.2, CMAC of the wing equal to minus 0.02, CL naught equal to 0.2 and CMAC equal to minus 0.02. The numerical value of Cm naught of the wing, contribution of the wing to Cm naught about the CG of the aircraft is dash in 2 decimal places. So, CMCG can be written as CMAC plus CLW into XCG minus XAC. XCG minus XAC bar. This can be further written as CMAC plus CL naught of the wing plus dou CL by dou alpha into alpha W into x bar CG minus XAC. So, in this CMAC plus CL naught W into x bar CG minus x bar AC plus A, this dou CL by dou alpha is nothing but AW lift curve slope into AW into alpha W into x bar CG minus x bar AC. So this is the parameter which is independent of alpha, which is nothing but your Cm naught plus AW into alpha W into x bar CG minus x bar AC. Okay. So we have to find out what is Cm naught. Cm naught is nothing but CMAC of the wing plus CL naught of the wing into x bar CG minus x bar AC. Okay. CMAC of the wing is nothing but they are given minus 0.02 minus 0.02 plus CL naught of the wing is nothing but 0.2. X bar CG value they are given it as 0.4. X bar AC they are given it as 0.3. 0.4 minus 0.3. So it is minus 0.02 plus 0.2 into 0.1, which is 0.02, that is equal to 0. So Cm naught value becomes equal to 0. Okay. So answer for this question is 0. Any doubt? If you have any doubt, you can ask. Otherwise, we'll wind up today's section. If you have any doubt, you can ask. Otherwise, we'll wind up today's section. Okay. Thank you. Good night.
Hello, sir.
Yes, you have some doubt?
Yeah, sir. Today, when I was solving one problem, I had one doubt, sir. Question is,
There is some
the
background
flight
noise
test,
behind you.
sir.
There is some background noise behind you.
Sir, I will send it through WhatsApp, sir. Otherwise.
Okay, okay. Yeah, you can ask otherwise, no issue.
Yeah, in a level flight at cruise altitude, CD is equal to 0.025. With a drag coefficient at 0 lift, CD naught
CD
is
not
equal to
equal to
0.018, sir. CD naught.
okay.
CD is equal to 0.025. CD naught is equal to 0.018.
Okay.
For 30-degree level turn, at the same altitude